Hi everybody, we're back and we're going to do another simulation today. Now, I took all of the M&Ms that we had yesterday, put those away, and today what we're going to do is we're going to talk about Reese's Pieces. I'm sure you guys are familiar with these. So what you want to do is find online the worksheet talking about sample distributions day 2, and we're going to talk about Reese's Pieces, how many candies there are and everything in the bag. And if we were in school today, believe it or not, everyone was going to get a bag of these. If you have a peanut allergy, I would have given you M&Ms or something different, but no black beans and white beans. We actually used Reese's Pieces here today. What we're going to do is notice that Reese's Pieces have 3 different colors. There's orange, black, and yellow. And if I had you guess which color you thought had the most candies, would there be more orange in the bag, more brown, or more yellow? What would you guess? Now, in years past when we did this activity, most people would take this bag, and once I let them guess, they would open it up and they would pour them out. But beforehand, we had people who would guess there'd be more orange than anything else. Some people said there'd be more yellow. Other people thought brown, for whatever reason they had. What a lot of people end up coming up with, though, is they thought that because there was 3 colors, why wouldn't they just use each color the same amount? So 1/3 of each one. So they kind of thought, well, they'd be equal, which is a fairly good guess. And, we'll figure out what's going on from there. So they thought that 1/3 of each color was there, maybe, which would be about a ratio of 1/3, which is 0.3 repeating. So they picked 0.33 would be orange, 0.33 is brown, and 0.33 is yellow. Now, the next question is, when I actually handed out the bags, before I had people open them, I'd say, now, when we open up these bags, everybody's going to pour them out, and there's way more than 25 in a bag, but if I had you randomly pour out 25 without paying attention to color, put them in, let's say, a cup like I have here, would you think that everyone in the class would have the same number of orange? Just to make it easy, we're going to talk about orange today. And you'd say, well, probably not, because like my answer says here, sampling variability from each bag would suggest that there's a slightly different number of orange candies in each one. In fact, if the same person took 25 candies out of the bag, counted the orange, put them back in the bag, and then poured it out again and picked 25 all over, you might not have the same number of orange from the same bag. That is our sampling variability. So let's pretend that 10 different students did this, and I had you write down a guess. How many M&Ms or how many Reese's Pieces do you think are orange? So there were 10 boxes in your notes, and you just wanted to write down a number. So I just kind of thought, well, 1/3 of 25 is about 8.3 repeating. So I would guess somewhere between 8 and 9 in each bag. So I went 8, 9, 8, 7, 8, 8, 10, 6, 10, 8. And you could pick any numbers you want. You could put 1, 2, you could put 24, 25, depending on what you thought would happen. The whole point here was that I doubt anyone would write the same number 10 times. That's because what we're seeing here is we're demonstrating the variability you expect in the number of orange candies in 10 different samples of 25 candies. So at this point, what I would have you guys do is take your bag, count out 25 M&Ms like I did here, and then you'd simply count how many of them are orange. And when you first put them in there, you try not to pay any attention to color, trying to be random. And once we did, then we would check to see how many orange there were. Now, I did this morning. That's right here and here. And what I got was I had 15 were orange, 6 were yellow, and 4 were brown. That's 25 total. And then my proportion would just be, because there's 25 in the cup, I did 15 divided by 25 gave me 0.6. 6 divided by 25 is 0.24. 4 divided by 25 is 0.16. And 25 divided by 25 is 1. So you can see these add up to 25. These add up to 1. So we have everything accounted for. Now that you've taken a sample of candies and you see the proportion of orange, make a second conjecture. Make a second guess. If you took a sample of 25 Reese's Pieces candies and found out that you only had 5 orange, would you be surprised? Well, based on my sample, just the sample I have here, because I got 15 the first time I did it, I'd be surprised if I only had 5 the next time. It seems to me like 5 is an unusually low number out of how many I had from the sample that I drew. Now, if I got 5 yellow, I wouldn't be surprised, or 5 brown, I wouldn't be surprised, because 5 is pretty close to what I had here, but 15 might not be. Going from 15 to 5 seems like quite a drop. Now, maybe that's just a sampling variability. Maybe I would have 5 next time. Maybe if we did this activity, some people actually would have 5, and they wouldn't be surprised. You just want your answer here to match with what happened with what you got. So what we then did was we were going to put our sample proportion on a Post-it note like the last one. We're going to place it on a number line and put it up on the board. I did this already. I did a simulation and I kind of wrote it out, and these are the numbers I got. So pause it if you need to, and you can jot those down and then find out that I actually did the summary statistics. I had a mean of 0.507, a standard deviation of 0.118. Now they wanted you to estimate the average proportion of orange, and that would be 0.5 would be my estimate. I would get rid of the 0.07. I actually just used the exact number here because I had it. So for part 2, what we want to do is talk about comparing the sample statistics to the population parameter. The population parameter is the true number of what color we should get in each bag. Now, usually, and if you take AP Stats next year, you'll find out we don't usually know population parameters. We don't know the true mean or the true proportion of candies that there are. Not in a bag, not in all the M&Ms or Reese's Pieces at Tops, not at all of them in the company, because we just don't usually know that information. But what we can do is we can use a sample and try to predict how many there are. So the proportion we had was what we call the sample statistic. And like we said, no, not everyone in the class had the same sample proportion. Some people had more orange, some people had less, some people did have the same. If I ask you to describe the variability of the distribution on the board, that's really talking about that dot plot we did. You'd be able to say now, after our notes from a couple days ago, it looks like the normal model. You can still use the word bell curve if you want to. It looks normal. It's mostly normal. It was centered around 0.5, and the spread had, I went with just the range. It went from 0.28 to 0.76. So that's my distribution of sample proportions. And like we talked about before with the normal model, we know we can go plus and minus 2 standard deviations from the mean, and that's the 95% confidence interval. Now, we haven't called it a confidence interval yet. We'll talk more about that next year as well. But we know that the 68, 95, 99.7 rule tells me that if we have a normally distributed set of data, that 95% of them, 95% of the data points will fall within 2 standard deviations of the mean, which really tells me if I know what my mean is, and I know what my standard deviation is, I can add the 0.118 twice to 0.507. That would give me my upper bound. And then I would subtract 0.118 from 0.507 twice. Well, technically, I'd only subtract it once and then take my new number and subtract it again. But you get my point. That would give me my lower bound. What that does then is it gives me my overall confidence interval. If you take that confidence interval and you cut it in half, we call that the margin of error. Now, because we're going 2 standard deviations to the left and 2 to the right, that's really 4 standard deviations we're moving, 2 left, 2 right. Since we're cutting that in half, the margin of error is easiest to know that the formula for this course is just 2 times the standard deviation. So whatever the standard deviation is, just double it. That's our margin of error for a 95% confidence interval. So if I look up here, if I take 0.112, I get 0.236. That would be my margin of error. And especially with things happening right now with elections and everything coming up, you probably see margin of error reported when you see polls that were done by Channel 2, Channel 4, Channel 7 News. And that's kind of some of the information we'll talk about with Algebra 2 next year as well. So let's talk about the simulation of the sampling process. Because you're not here, I think this is better. Again, I have the link in Classroom for you to see, and you can go there. And what we can do is we can actually run this test. And I'll explain this 0.5 to you in a minute in the next page. But let's go ahead and take 25 candies like we did before. And we draw one sample. Let's start at the back of the classroom this year. We'll go, or this lesson. Let's say Robert, this is Robert's sample. When we draw a Robert sample, he's going to go ahead and take his 25 Reese's Pieces, and we see he gets 10 out of the 25, which would go right here. Again, we're looking at proportion, so I'll change that to a proportion. He's at 0.40. Before him, I think we have Dominic Townsend. Dominic does the same thing. He also gets a proportion of 0.36. Elizabeth, hi Elizabeth, how you doing? She draws the same thing. This time she gets a ratio of 0.44. Let's go ahead and add 27 more to this. That'll be me and the other 26 people in the class. We'll draw the samples and see what happens. I can actually hide the candy machine and show the summary statistics, and you can see that this is what we have when we use a sample size of 25 candies and we draw it 30 times. So there's 30 dots up here, and each of these dots represents 25 candies. And of those 25 candies, it really represents how many of them are orange. So you can see the most we had was over here. Again, I could change it to counts if you want to. And you could see the most someone got 19 orange M&Ms. Someone else got 7. That's the lowest and the highest I got. You can kind of see, and I can show you here. That's what the normal model would look like, but I'm pretty far from that because I don't have enough data points. But you can see how this is starting to have like a mound shape here, where we have very few points on the extremes and more in the middle with our heights higher. So that's really my question for you then. How do you think I can take this and make it look more normal? How can I make it so it fits better in that spot? Well, that's actually what the next page in our notes is talking about. With part 4, we're going to examine the role of sample size, and using the simulation, we're going to change it from 25 to 50 to 100, then 1,000, and watch what happens when we run that simulation with that many. Now, I need to ask you to be patient because it does go a little bit slower when it has that many of them. But just so you know, when you look up the information about Reese's Pieces, they actually tried to design the colors of the Reese's based on this label. You'll notice the bag is more orange than anything else, and then there's yellow and the browns. They actually tried to coordinate it with the colors on the package. They have the majority of the candies are orange, 50%, 25% are yellow, and 25% are brown. So what we're looking for is to see what happens when we do that. But we're going to change our proportion size. So let's go ahead and run the same thing with 50. And we'll see what happens here. We'll do our summary stats as well. You can see that when I do 50, I'll just jot these down real quick. When I had a sample size of 50, my mean ends up being 0.535, and my standard deviation is 0.074. I think the next thing they wanted me to do was do 100 and then 1,000. So I'm going to go ahead and reset this. I'm going to draw 100 candies this time. And you can see that my mean is 0.505. My standard deviation is 0.050. And then one last thing, let's go ahead and run it 1,000 times. I can reset this so they're not there. Do it 1,000 times, draw my sample, and see what happens. And you can see that my mean with 1,000 of them is 0.502, and my standard deviation is 0.013. So going back and looking at this information, how close are the proportions, my mean, obtained in the class to the population parameter of 0.50? Well, with my original one, when we did it in the class, I had 0.507, so I was pretty close. As I increased my sample size to 50, I went to 0.535. That's a little farther away. And then with 100, I went to 0.505. That was really close. And then I went to 0.502, got even closer. So we got really close to my mean with having a larger sample size. Then my standard deviation started at 0.116 or 0.118, I think it was, and went to 0.074. Increased the sample size, went to 0.050. And then with my 1,000, I ended up having a standard deviation of 0.013. So it got really small. This really just kind of reinforces what we said yesterday. As the sample size increases, the standard deviation decreases, and the variability also decreases. So finally, what we want to do is say, if your proportion falls outside the 95% confidence interval, remember 95% confidence interval talks about 2 standard deviations from the mean. You can even notice with our pictures up here, when we do that, when we look at it here, let me see if I put my normal approximation on there. Let me do more than the 30 people in class. Let's do 300 of these. We'll draw the sample. And you can see how it starts to look more